Stress testing Kali Linux. Armand Shahriarian. Stress testing. Some software, and even hardware, has a hard time handling enormous loads. There are many reasons for this. In the case of hardware, such as devices that are purpose-built or devices that fall into the category of Internet of Things, IoT, there may be several reasons that it can't survive a lot of traffic. The processor that's built into the network interface could be underpowered because the design of the overall device never expected to see a lot of traffic. The application could be written poorly, and even if it is built into the hardware, a poorly designed application can still cause problems. As a result, it's important for security testers to ensure that the infrastructure systems they are responsible for will not simply fall over when something bad happens. It may be easy to think of stress testing as flooding attacks. However, there are other ways to stress applications. One way is to send the application unexpected data that it may not know how to handle. There are techniques to specifically handle this sort of attack, so we're going to focus primarily on overwhelming systems here and deal with fuzzing attacks, where we specifically generate bogus data, later. Having said that, though, in some cases network stacks in embedded devices may not be able to handle traffic that doesn't look like it's supposed to. One way of generating this sort of traffic is to use a program called FragRoot. The program FragRoot, written many years ago by Doug Song, takes a series of rules and applies them to any packet that it sees destined to an IP address you specify. Using a tool like FragRoot, you can really mangle and manipulate packets originating from your system. These packets should be put back together again, since one of the main functions of FragRoot is to fragment packets into sizes you identify. However, not all systems can handle really badly mangled packets. This may especially be true when the packet fragments are coming in with overlapping segments. With IPPAC ETS, the IP identification field binds all fragments together. All fragments with the same IP identification field belong to the same packet. The fragment offset field indicates where the fragment belongs in the overall scheme of the packet. Ideally, you would have something like bytes 0 to 1200 in one packet fragment, and the offset in the second fragment would start at 1201, indicating that it's the next one to be put back together. You may get several more of roughly the same size, and the network stack on the receiving end puts them all together like squares in a quilt until the quilt is whole. If, though, we have one fragment that says it starts at 1150, and we assume a transmission unit of 1200, but the next one says it starts at 1201, there is a fragment overlap. The network stack needs to be able to handle that event correctly and not try to put overlapping packets together. In some cases, dealing with this sort of overlapping behavior has caused systems to crash because they just can't deal with the conflicting information they are receiving. Example 2 to 3 shows a configuration file that can be used with FragRoot to generate potentially problematic traffic. Example 2 to 3. FragRoot configuration. The first line indicates that IP packets should be interleaved with duplicates. The 7-in That line indicates to set the time to live field at 7 hops. This can cause packets to be dropped in transmission. The second line says to fragment IP packets at a packet size of 64 bytes. The new tells FragRoot to overlap packets by favoring new data rather than old data. 33% of the time, we are going to drop packets. 40% of the time we are going to duplicate random packets. FragRoot is also going to randomize the order that packets hit the wire, which means nothing will be in the correct sequence, ideally, when it hits the endpoint. Finally, the details are printed, indicating what was done to the packet that was received. In order to use this, we would use FragRoot ffrag.rules. 192.168.5.40. In this example, the name of the rules file is frag.rules and 192.168.5.40 is the target to which we want to send garbled traffic. These parameters can be changed to suit your own particular setup. Using a tool like FragRoot with a set of rules like this will likely mean nothing useful. We'll end up at the target. However, that's not really the point. The point is to check your target and see how it's handling what it is receiving. Are the packets just being discarded? Is the operating system behaving correctly? This part is essential. Just knocking things over isn't helpful. You need to be able to document the behavior so you can provide some indications of what may need to be done. Documenting your efforts in as detailed a way as possible is important in order to be successful and asked back or retained. Ethics warning. You need to ensure that the systems you are working on especially when there could be damage or disruption, and just about everything we will be talking about has that potential, are either yours or systems you have permission to be testing. It's unethical at a minimum and likely even illegal to be testing any system you don't own or have permission to be testing. Testing, no matter how simple it may seem to be, always has the potential to cause damage. Get your permission in writing, always. Once you have the configuration set, you can run FragRoot on the system where you are originating traffic. If you can use it on a device that is capable of routing, you can manipulate traffic passing from one network to another, but this is generally going to be something to test from a single system. Testing out the fragmentation on my local network, I used the command line in example 2 to 4 and received the results that you can see. The testing of the system was done by just issuing ping requests to the target. I could have just easily done testing against another system using traffic like web requests. Example 2 to 4. FragRoot output using rules LE. Root at Kali #FragRoot ffrag.rules 192.168.86.1. The interesting thing we see in this test is the floating point error. This happened in FragRoot from just manipulating the traffic. This particular testing appears to have turned up a bug in FragRoot. The unfortunate thing is that once the floating point error happened, network communication stopped. I was no longer able to get any network traffic off my Kali box, because of the way FragRoot works. All traffic is set up to run through FragRoot, but when the program fails, the hook doesn't get unset. As a result, the operating system is trying to send network communication to some thing that just isn't there. This is another example of the reason we test. Software can be complex, and especially when underlying libraries have changed, behaviors can also change. Ultimately, any failure resulting from a stress test is a problem with availability. If the system crashes, no one can get to anything. If the application fails, the service isn't available to users. What you are performing is a denial of service attack. As a result, it's important to be careful when performing these sorts of attacks. There are definitely ethical implications, as noted earlier, but there are also very real possibilities to cause damage, including significant outage to customer-facing services. More on that in a moment. A simple way to do stress testing is to use a tool like Hoping 3. This fabulous tool can be used to craft packets on the command line. Essentially, you tell Hoping 3 what you want different fields to be set to, and it will create the packet the way you want. This is not to say that you need to always specify all of the fields. You can specify what you want, and Hoping 3 will fill the rest of the fields in the IP and transport headers as normal. Hoping 3 is capable of flooding by not bothering to wait for any responses or even bothering to use any waiting periods. The tool will send out as much traffic as it can, as fast as it can. You can see the output from the tool in example 2 to 5. Example 2 to 5. Using Hoping 3 for flooding. Root at Rosebud #Hoping 3 flood SP8192.168.86.1. When I ran this, I was connected to my Kali system remotely. As soon as I started it up, I tried to kill it because I had the output I was looking for. However, the system was cramming packets down the wire, and getting responses, as fast as it could. This made it hard to get the Control-C I was trying to send to my Kali system, meaning Hoping 3 wasn't dying, it was just merrily sending a lot of packets out into the network. Fortunately, I used my local network to test on, rather than trying to test someone else's system. The operating system and network were otherwise engaged, so there was no response for a long period of time. In example 2 to 5, I am using Hoping 3 to send SYN messages to port 80. This is a SYN flood. In this example, I'm not only testing the ability of the system to handle the flood at the network stack, operating system, with just the capability of the hardware and operating system to respond to the traffic, but also testing the transport layer. The operating system has to hold out a small chunk of memory with Transport Control Protocol (TCP) connections. Years ago, the number of slots available for these initial messages, called half-open connections, wasn't very large. The expectation was that the connecting system was well behaved and it would complete the connection, at which point it was up to the application to manage. Once the number of slots able to take half-open connections is exhausted, no new connections, including connections from legitimate clients, will be accepted. These days, most systems are far more capable of handling SYN floods. The operating system will just handle these inbound, half-open connections and dispose of them using a variety of techniques. including reducing the timeout period during which the connection is allowed to be half open. This test uses SYN messages, S, to port 80, P80. The idea is that we should get a SYN/ACK message back as the second stage of the three-way handshake. I don't have to specify a protocol because that's accomplished by just saying that I want to send a SYN message. TCP is the only protocol that has the SYN message. Finally, I tell Hoping 3 that I want it to use flood mode, -flood. Other command line flags will do the same thing by specifying the interleave rate, the amount of time to wait before sending the next message. This way is easier to remember and also pretty explicit. The program Hoping has been through a few versions, as you can likely guess from the use of the 3 at the end. This tool is commonly available across multiple Linux distributions. You may call the program by Hoping on some systems, while on others, you may need to specify the version number Hoping 2 or Hoping 3, for instance. Testing at the lower layers of the network stack using tools like Hoping 3 can lead to turning up issues on systems, especially on more fragile devices. Looking higher up in the network stack, though, Kali Linux has numerous tools that will tackle different services. When you think about the Internet, what service springs to mind first? SPO? Ti? Facebook? Twitter? Instagram? All of these are offered over HTTP, so you're interacting, often, with a web server. Not surprisingly, we can take on testing web servers. This is different from the application running on the web server, which is a different thing altogether and something we'll take on much later. In the meantime, we want to make sure that web servers themselves will stay up. Although Kali comes with tests for other protocols including the Session Initiation Protocol, SIP, and the Real-Time Transport Protocol, RTP, both used for voice over IP, VoIP. SIP uses a set of HTTP-like protocol commands to interact between servers and endpoints. When an endpoint wants to initiate a call, it sends an invite request. In order to get the invite to the recipient, it will need to be sent through multiple servers or proxies. Since VoIP is a mission-critical application in enterprises that use it, it can be essential to determine whether the devices in the network are capable of withstanding a large number of requests. SIP can use either TCP or User Datagram Protocol, UDP, as a transport, though earlier versions of the protocol favored UDP as the transport protocol. As a result, some tools, particularly if they are older, will lean toward using UDP. Modern implementations not only support TCP but also support Transport Layer Security, TLS, to ensure the headers can't be read. Keep in mind that SIP is based on HTTP, which means all the headers and other information are text-based, unlike H.323, another VoIP protocol, which is binary and can't generally be read visually without something to do a protocol decode. The tool InviteFlood uses UDP as the transport protocol, without the ability to switch to TCP. This does, though, have the benefit of allowing the flood to happen faster because there is no time waiting for the connection to be established. In example 2 to 6, you can see a run of invite flood. Example 2 to 6. SIP invite flood. Root at rosebud hashtag invite flood eth0 kilroydummy.com 192.168.86.238 150,000. We can break down what is happening on the command line. First, we specify the interface that invite flood is supposed to use to send the messages out. Next, is the username. Since SIP is a VoIP protocol, it's possible that this may be a number, like a phone number. In this case, I am targeting a SIP server that was configured with user names. Following the username is the domain for the username. This may be an IP address, depending on how the target server is configured. If you don't know the domain for the users, you could try using the IP address of the target system. In that case, you'd have the same value twice, since the target is the next value on the command line. At the end is the number of requests to send. That 150,000 requests took seconds to send off, meaning that the server was capable of supporting a large volume of requests per second. Before moving on to other matters, we need to talk about IPv6. While it isn't yet commonly used as a network protocol across the Internet, meaning I couldn't send IPv6 traffic from my system to, say, Google's website, the time will come when that should be possible. I mention Google in particular because Google publishes an IPv6 address through its domain name system, DNS, servers. Beyond being able to send IPv6 through the Internet, though, is the fact that some enterprises are using IPv6 today to carry traffic within their own enclaves. However, even though IPv6 is more than 20 years old, it has not had the same run-in time that IPv4 has had, and it took decades to chase some of the most egregious bugs out of various IPv4 implementations. This is all to say that in spite of the time that operating system vendors like Microsoft and the Linux team have put into development and testing, more real-world testing across a wide variety of devices is still needed to be comprehensive. This is all to say that Kali includes IPv6 testing tool suites. There are 2 of them, and each suite has a good-sized collection of tools because in the end, IPv6 includes more than just changes to addressing. A complete implementation of IPv6 includes addressing, host configuration, security, multicasting, large datagrams, router processing, and a few other differences. Since these are different functional areas, multi-PLE scripts are necessary to handle those areas. The way IPv6 behaves on the local network has changed. Instead of the address resolution protocol, ARP, being used to identify neighbors on the local network, IPv6 replaces and enhances that functionality through new Internet Control Message Protocol, ICMP, messages. Coming with IPv6 is the Neighbor Discovery Protocol, which is used to help a system connecting to the network by providing details about the local network. ICMPv6 has been enhanced with the router solicitation and router advertisement messages as well as the neighbor solicitation and neighbor advertisement messages. These 4 messages help a system to get situated on a net Work with all the relevant information needed, including the local gateway and domain name servers used on that network. We will be able to test some of these features to determine how a system might perform under load, but also by manipulating the messages in ways that may cause the target system to misbehave. The tools NA6, NS6, RA6, and R6 all focus on sending arbitrary messages to the network by using the different ICMPv6 messages indicated previously. Whereas most systems will provide reasonable information to the network. To the best of their knowledge and configuration, these tools allow us to inject potentially broken messages out to the network to see how systems behave with such messages. In addition to those programs, the suite provides TCP/6, which can be used to send arbitrary TCP messages out to the network, allowing the possibility of TCP-based attacks. No matter what sort of stress testing you are doing, it's important to keep as many notes as possible so you can provide detailed information as to what was going on.